Welcome to the turbomachinery course. In this course, we'll be covering the details about turbo machines, how they work, and different types in 6 units. The slide shows all the 6 units and the books that you can follow for this course. Coming to Unit 1. In Unit 1, we will be covering introduction and classification of turbo machines, work done by turbine or compressor, governing equations, and expansion and compression processes. Coming to introduction of turbo machines are devices that help in transferring energy of the fluid to that of mechanical parts, and in general, fluids being gas or liquid, they transfer their energy to mechanical parts, in return help them to rotate, and vice versa. The applications of turbo machines are plenty in real life or day-to-day life, including fluid transportation, energy conversion, power generations, etc. etc. Now coming to classification of turbo machines can be broadly classified into two main categories: turbines, pumps, or compressors. What are turbines? Turbines are devices that convert hydraulic energy of the fluid to mechanical energy. Basically, the fluid will come, expend some energy, and in return move or rotate a mechanical part, thereby giving mechanical energy to the mechanical part. There are different types of turbines. First being steam turbine. These are the turbines which use steam as the working fluid. The energy of the steam is being transferred to the mechanical parts to generate mechanical work. They are widely used in power plants for electricity generation. Coming to the gas turbines. Gas turbines operate on the principle of Brayton cycle, and they use a mixture of air and fuel as the working fluid. They are used mostly in aviation, power generation, and many other industrial applications. Coming to the hydroelectric turbines. These are the turbines which use the kinetic energy of flowing water to generate mechanical work. They are mainly used in hydroelectric power plants. Coming to the wind turbines, as the name suggests, converts the kinetic energy of wind into mechanical energy. They are also used for electricity generation. Coming to the jet engines. Jet engines are a form of gas turbine that generates thrust by expelling high velocity exhaust gases. Now, just like turbines, pumps and compressors are also turbo machines, but here the devices, instead of taking energy from the fluid, they add energy to the fluid. Here it is just the reverse principle of turbine. Here the mechanical part rotates or gives motion to the fluid, and in return adds energy to the fluid being gas or liquid. Now when the working fluid is a liquid, we use a pump, and when the working fluid is a gas, we use a compressor. But the working principle of both pumps and compressors are quite similar. Now, there are different types of pumps and different types of compressor. Coming to the types of pumps, centrifugal pump. In centrifugal pumps, centrifugal force is used to move the fluid from center of the impeller to the outer edges. They are mostly used in industries for fluid transport. Positive displacement pump. These pumps use mechanisms like pistons, gears, or diaphragms to displace a fixed volume of fluid with each cycle. Examples include reciprocating or rotary pumps. Now coming to types of compressors. Axial flow compressors. Axial flow compressors increase the pressure of the fluid by causing it to flow in axial direction. They are used in gas turbines and jet engines. Centrifugal compressors. Similar to the centrifugal pumps, centrifugal compressors use centrifugal force to increase the pressure of a fluid. Mind it, here the fluid being gas. They are used in various industrial applications. Now coming to the reciprocating compressors. Reciprocating compressors use pistons to compress the gas. They are used in applications requiring high pressure, such as refrigeration. Scroll compressors. They use two interlocking spirals to compress the fluid. They are mostly used in air conditioning and refrigeration systems. Now coming to the governing equations that we use are on the principle of which the turbo machines work. So the governing equations that govern the working of turbo machines are continuity equation, momentum equation, energy equation, Euler's equation, etc. In general, all these equations govern the functioning of turbo machines. All these equations will be covered in detail in the course. Here we'll just see briefly what are these equations and what they mostly comprise of. First one being continuity equation. This equation states that the mass flow rate into a control volume must be equal to the mass flow rate out of the control volume. Basically, it speaks about the mass balance. How much mass of the fluid or water or gas is coming into a system or control volume, that much amount of fluid or mass should leave the system or control volume. Coming to the momentum equation, this equation states that the sum of the forces acting on a control volume must be equal to the change in momentum of the fluid within the control volume. F is equal to ma, force is equal to mass into acceleration, which is the Newton's second law. It is briefly the theoretical statement for that. Coming to the energy equation. This equation states that the sum of heat transferred to the fluid or the work done on the fluid and the change in internal energy of the fluid must be equal to 0. It is basically the first law of thermodynamics stated in a theoretical form. Coming to the Euler's equation. This equation is a special case of momentum equation for incompressible fluids. It states that the change in total head of the fluid as it flows through a turbo machine is equal to the change in kinetic energy of the fluid plus the change in pressure energy of the fluid. The general form of this is being studied as Bernoulli's equation, where we say wherever the fluid is, the pressure head, the potential head and the kinetic head, the sum of these are equal. These equations are used to analyze the performance of turbo machines and to design turbo machines. In addition to these governing equations, there are other equations that are used in analysis of turbo machines. These equations include equations of state for the fluid, equations of heat transfer, and equations of turbulence. The analysis of turbo machines is a complex and challenging task. However, the governing equations provide a foundation for this analysis and allow engineers to design and optimize the turbo machines for a variety of applications. Now we will discuss the working principle of turbine in brief. As we know, turbines are the devices that extract energy from a fluid's flow and convert it into mechanical work or mechanical energy. Now, the principle of turbine, in the working principle of turbine, there are various parts used. There will be a fluid inlet, there will be some nozzles or guide vanes, there will be blades or rotors, and among these devices or among these parts, the energy transfer will occur. So we will discuss all these parts little briefly in this slide. The fluid inlet. The fluid, often referred to as the working fluid, it can be liquid or gas, enters the turbine at a certain velocity and pressure. Then there are nozzles or guide vanes. The fluid passes through a set of stationary nozzles or guide vanes. This component helps direct the fluid onto the turbine blades at the correct angle and optimizing the energy transfer. Now coming to blades or rotors. The fluid then interacts with a set of rotating blades or rotor assembly. This high velocity fluid imparts kinetic energy to the blades as it flows over them. Coming to the energy transfer, the kinetic energy of the fluid is converted into mechanical energy as the blade rotates. This rotation drives a shaft connected to a generator or compressor or other machinery, producing useful mechanical work or electricity. Then there is outlet. After passing through the blades, the fluid expends all the energy, then it has to exit the device or the turbine at a reduced velocity and pressure. In some cases, it may still have residual kinetic energy which can be further utilized in downstream processes. This is a diagram shows the whatever we have discussed in the principles or working principle of turbine. This is the inlet where the water comes in, that is the working fluid comes in. It is being guided and it hits the blades. These are the guide vane, then it hits the blades and it imparts its energy, kinetic energy, onto the blades, thereby rotating the blade. Now this is the internal or the cross-sectional view of the turbine. What happens that these blades will rotate this shaft. We can say now this shaft is connected to a generator or compressor or any other mechanical devices you can generate, because already there's rotors that are rotating, they are rotating the shaft, and the kinetic energy of the fluid has already been converted to mechanical energy of the shaft. Now whatever the shaft is connected to, that energy will be transferred to that machinery or that device, thereby converting the kinetic energy of the fluid to mechanical energy. Working principle of compressors. Compressors are devices that increase the pressure of the fluid by adding energy to it through mechanical work. It works exactly opposite to that of the turbine. In turbine, we take energy from the fluid and give it to the mechanical parts, whereas in compressor, we take energy from the mechanical parts to give to the fluid, whether it is gas or a fluid or a liquid. Now, here also various parts are there, like fluid inlet, rotating blades or impellers, diffusers or stators, energy addition, where the process of addition will occur, including all these parts, and then finally the outlet. Now, in the fluid inlet, the fluid enters the compressor at a specific velocity and pressure. The rotating blades or impellers are set of rotating blades that accelerate the fluid and impart kinetic energy to it. Now it is opposite to that of the turbine, so here the fluid will come at a very low velocity and pressure, and when it is being rotated by the blades and impellers, its energy is being added. Then the fluid is passed through stationary diffusers or stator blades. These components convert the kinetic energy into pressure energy, thereby increasing the fluid's pressure while slowing it down. They won't increase the kinetic energy, they will rather increase the pressure energy. They will add energy to the fluid in terms of pressure energy. Now, energy addition may happen in multiple stages or a single stage. This process of acceleration and pressure increase is repeated in successive stages with alternating sets of rotating blades and stator blades. This helps in achieving higher pressure ratios. Now finally, after all this energy addition, the final fluid will exit the compressor or the device at a very high pressure and temperature compared to the inlet. It's then directed to the next stage of the system, such as combustion chamber in gas turbines or further processing in industrial applications. Now this shows the working of a compressor. This is a centrifugal compressor, whereas this is a reciprocating compressor. We will discuss little bit of both, how they are increasing the pressure of the fluid. Minded in compressors, the fluid being air. But the similar kind of principle works for pumps as well, where the working fluid is liquid. Now first coming to the centrifugal compressor, which is shown on the left side of the slide. Number 1 shows the rotating rotor or rotating parts or blades. In compressor, first the rotating parts will be rotated and the fluid will come through the inlet. The fluid is coming and it is filling up the gaps of the rotating part. As the rotating part moves, they impart energy or they give their energy to the fluid, increasing its speed. But then it is allowed to move through the outlet, where it is allowed to move into a small volume. Thereby, the speed of the fluid is reduced and the kinetic energy is forced to convert to or stored as pressure energy. So here it shows first spinning rotor is off center, so that first the volume of the fluid that is coming in, that will be more, and as the fluid is moving through the rotors, then the volume will be compressed, thereby converting the kinetic energy to the pressure energy. Arms with self-adjusting length create cavities of varying size. these rotors or blades or vanes, they have adjusting length so that this volume can be adjusted as the rotor follows the cavity geometry. Then the air fills the cavity and travels around. The air comes in, it fills first the higher volume, and then it is being guided towards the more constricted space by the guiding vanes or the rotors. As the cavity gets smaller, air pressure goes up. So the rotating parts impart the kinetic energy on this air and force it to increase its pressure by guiding it to smaller volumes. And finally, the pressure of the gases increase and they are being exit through the outlet. Air is forced out through the output. Now, mind it, this air can be used in tires of vehicles or for refrigeration process or for many other industrial applications. And this is how the centrifugal compressors work. Similar kind of principle is used for centrifugal pumps, only the working fluid will change. It will vary, it will change from air to being fluid. So fluid means liquid. So in water also same thing, the water will come in. It will fill up the empty spaces, that is a higher volume guided by the vanes, and as the fluid is rotated by the guiding vanes, it will be pushed into smaller volumes, thereby increasing its pressure, and when the pressure is increased, it will be let out of the compressor. Now coming to the working principle of the reciprocating pump, here it is pretty straightforward. The air comes in and it is being compressed forcibly by the piston arrangement, and this is a positive displacement compressor. Pump also works on the same principle. So what happens? First, the flywheel will rotate, the rotor spins or flywheel will rotate. This will be connected to the piston through a series of crankshaft and connecting rod, the mechanical parts, that will move the piston up and down, move this piston up and down. Then there will be an inlet that will pull in. When the piston moves down, a suction is created. This will open the valve, the inlet valve, through which the outside air will be pulled into the chamber or the free space or the vacuum space. And as the piston moves up, this valve will be closed. Being a one-sided valve, it will be closed, and the air will get trapped inside this chamber, thereby being compressed by the piston as the piston moves up. Now when the piston moves to the top dead center or reaches the extreme top, this air will be fully compressed and it will exert pressure on the outlet valve, which is again a one-way valve which will open only towards the outside direction. Here the inlet valve being opening to only in the inward direction will be kept closed by the compressed air, whereas the compressed air will put force on this outlet valve or exhaust valve and it will be forced open, and this compressed gas will be released and forced out of the system or the compressor and will be stored in a storage tank, which can be later used for any of the industrial applications. Now these are the working principles of compressors which we discussed briefly. Basically we covered what are in unit 1 in very brief. Again, let's revise. Unit 1 covers introduction and classification of turbo machines, what are their types, then work done by turbines and compressor, and governing equations. Finally, we have to see how expansion and compression processes are happening. For that, we have to see what is expansion process and what is compression process. Coming to the expansion process. Expansion process happens in turbines, compression process happens in compressors. So we are discussing these processes. Now in thermodynamics, the expansion process refers to the change in state of the substance as it undergoes a decrease in pressure while doing work on its surrounding. This process can occur in various contexts such as in piston cylinder arrangement, a turbine, or even in natural phenomena like the expansion of gases. So here, since we are discussing about turbine, so whatever process is happening in turbine, that is an expansion process. In thermodynamics, an expansion process is a process in which the volume of the system increases. So this can happen due to a number of reasons like decrease in pressure or increase in temperature or removal constraints on the system. So basic concept being, when a substance expands, it typically does work on its surrounding, pushing against an external work. Now mind it, in turbine, the fluid comes in and does work on the mechanical parts, hence it's an expansion process. This work can manifest as mechanical work like lifting a weight, or as other forms of energy transfer such as movement of a piston or the spinning of the turbine. Now, where are the applications? The applications of expansion process in real world scenarios include steam turbine, internal combustion engines and refrigeration cycles. In steam turbine, the high pressure steam expands and does work as it passes through the turbine blades, which converts its energy into rotational mechanical energy. This is what we are discussing. This is what we are studying in these turbo machines. In internal combustion engine, the expansion of gases produced by combustion pushes the piston down, converting the heat energy into mechanical energy. In refrigeration cycles, the expansion of the compressed gas results in cooling and allowing the gas to absorb heat from its surrounding. But we will be mostly interested in the steam turbine, where the expansion process is used to convert fluid energy or hydraulic energy into rotational mechanical energy. Now there are different types of expansion processes based on the type of thermodynamic cycle or process they follow. For example, isobaric expansion, isothermal expansion, adiabatic expansion and free expansion. In an isobaric expansion, the pressure of the substance remains constant during the process. As the name suggests, isobaric means constant pressure. This often occurs when a substance expands in an open system where it's in contact with constant pressure environment. Now coming to the isothermal expansion refers to an expansion process that occurs at the constant temperature. As the name suggests, isothermal means constant temperature. For an ideal gas, this involves maintaining temperature constant at constant value while allowing the gas to expand, resulting in a decrease in pressure and volume. Now coming to the adiabatic expansion involves an expansion process in which there is no heat exchange because it will be in an insulated environment. In this case, the substance is thermally insulated and the temperature of the substance decreases as it expands due to the conversion of internal energy into work. Coming to the free expansion, this is also known as Joule's expansion, occurs when a gas expands into a vacuum, without any external work being done on or by the gas. In this case, the gas internal energy remains constant and there is no heat exchange. Now, coming to the work done by expansion. The work done by any polytropic expansion where the polytropic exponent is being given by N is given by this formula. W, or the work done, is equal to Pi Vi minus Pa by 1 minus N, where Pi is the initial pressure, Vi is the initial volume, Pf is the final pressure and Vf is the final volume of the system. N being the polytropic exponent. For each of these processes, N can vary. Now coming to the compression process. Just like expansion process, compression process is opposite of expansion process. Here, a compression process is a process in which the volume of the system decreases, and this can happen due to a number of reasons like increase in pressure or decrease in temperature. Now the application of constraints on the system includes when a system is compressed, work is done on the system by its surrounding. The amount of work done is equal to the change in the volume of the system multiplied by the pressure exerted by the surrounding. The work done is similarly calculated similar to that of the expansion, only the work will be done on the system, not by the system. And there are different types of compression, same as that of the expansion. Here are few of them listed like isobaric compression, isothermal compression and adiabatic compression. In an isobaric compression, the pressure of the system remains constant while its volume changes. As the name suggests, isobaric means constant pressure. This can involve heat exchange with the surrounding to maintain the pressure while the volume decreases. Isothermal compression, as the name suggests, isothermal means constant temperature. Now, in an isothermal compression, the temperature of the system remains constant. This requires heat exchange to ensure that temperature doesn't change with volume when the volume is reduced. Now coming to the adiabatic compression, the adiabatic compression occurs when there is no heat exchange between the system and its surrounding during the compression process. Now this can lead to change in temperature as compression causes changes in internal energy. Mind it, adiabatic compression will happen in an insulated environment just similar to that of the adiabatic expansion. Now with this we covered all the aspects of unit 1 very briefly, what we were supposed to cover. So we covered almost every aspect of unit 1 very briefly, that is introduction and classification of turbo machines, work done by turbine or compressor, governing equations, expansion and compression processes. Next we will be discussing about unit 2. Thank you.